Okay, good morning. I think the last part, um, last discussion is this, right? And I think this is, I already fixed the calculations. If you see uh, the equilibrium, the sigma F and sigma M, I have fixed all of the informations, and then I think it is true that all the components now are clear. So you could see from the sigma F, and basically how it works is basically taking the equilibriums, taking the statics overview. Uh, First is we take the sigma F, and then by looking at this on this diagram on the bar one, you can see that we have the Cx and the tension at 1 or force at 1, F1 is supposed to be equilibrium with Dcx, which is it would be negative 80/3 when using the moment. Using the moment at here, then get F1 is negative, which means that we are going to have a tension or compression here, a compression. So we imagine a compression here, but it turns out to be negative, so it should be the other way around, it should be a tension. So the same idea for the force in x-axis and y-axis. We get all the components through this triangle. So we could define this triangle here, which we get the F4, and then F3 we also get the same thing here. Here F3 we get the same thing with this 4/5, and then on point B we get also here, since we know that we have the F2 and multiply with the 4/5 is the cosine, and this should be equal to the F3. So we get that the F2 will be 5/3. Okay, I think we get all the components, and we get here, and then the question is about the all the tension and compression. What would be the best loads when we have some stresses, and with compression and tension, it has different allowable stress, and then we could pick up the number, and then we pick the number that is going to be the lesser one. So since B1 is less than B2, B6, then we are going to take this as our allowable load. Okay, now I would like to move to the next subtopics, which is, I think, just a short mention about the Saint-Venant principle. So if you could see from the picture, this is how the concentrated load. Okay, so we have a concentrated load on the distribution of normal stress. So let me write here. So why this becomes our discussion? Because so far we treat distribution of the sigma or the normal stress uh, on cross section undergoing uniform axial deformation. So so far this is our assumption. All of the axial deformations are going to be uniform. However, near the load points, plane section do not remain plane. Or we say here that this normal stress is not uniform. So let's say we consider the short compression bar as in the picture here. So this is a short compression bar. So we imagine that it is being applied some loads. If we have the cross sections as A, or we can say the A is a base and the thickness or the height. And from this picture, we can have at least three statements that is related. So let me pick up this statement here. That the first one is that all the stress average or the sigma average, they are going to be the same, okay? The sigma average, that is going to be negative P over A, okay? Negative P over A. Why is negative? That's because it's just to mention that it is a compression. And then near the ends of the bar, where the concentrated load is applied, especially if we could see the figure B, there is a stress concentration with higher stresses near the point of the application. So if you could see, there will be a different distribution. So you can see that there will be some peak distributions on the image. And then if we take far away, so let's say we have, this is at B over 4, which means this is going to be in the center. This will be in the center, B over 4. So this would be B, and that is the distance B over 4. So it's not this. So that X is B over 4. So it should be this one. So what could that mean is at the center, or at when the load is applied, there will be a concentrated load like this one, which is very, very, if you see this is like 2 times or almost 3 times stress, B over A. But then if we could take the distance lower, B over 2, perhaps here, the peak, it seems that it's not really as clear as the B over 4, right? And if we see from the whole distance, we see it is uniform distribution. So what that means is that at distance from the point that are greater, so we think this is going to be further away than the width of the compression bar, which means this is the width, B, the stress distribution will be uniform. Okay. Now the third one here, this is what we call the Saint-Venant principle. Or if we take, so this one is the same principle. So what does it say? It says that stresses and strains in a body at points that are sufficiently remote, quite far from points of load, depend only on the static resultant of loads and not on the distribution of the loads. So the stress distribution at the picture here, at the right one, when x equal b, it would not greatly change or alter if the single load P at the bottom end of the bar were to be replaced by maybe P over 2 symmetrically applied on the bottom side. So it means that this single P, if we would like to change with this P over 2, it will be still, if we see from this point of view, this distance, this is still similar to the first one. So it's not going to be altered or changed. But however, if we are going to make the observation or the analysis only nearby this load, it means that we are going to have this condition. Okay. There will be some distribution differences between these nearby the single loads, okay, the distance, and the one that is quite far. So what this principle does is we can say that our expressions that we define and derive, they are valid, except at the very near points. Okay. So here the expressions we learn so far still valid, except very near to points of load or support. It could be also support, or if there are change in the cross section, or near to cross section that is abruptly change. Okay. Okay. Okay, so there are some sections on the Hooke's law for plane stress and relationship between the modulus of elastic for the Young's modulus and the shear modulus, which I introduce you with G. There are some notes here, but I think I will skip it for now. And we are going back here later on. And I would like to go for just a little bit on the definition of stress and strain in general. And then if we finish that, then we can go back and go for the Hooke's law and then finish chapter 2. So I think I will go for another one. Okay, now the general definition of stress strain. Before we move here, let me just add some appendix from the textbook, because we are going to encounter what we call as a inertia. So let me just give you some overview. What is moment inertia? Okay, I believe you know it in physics, but I think I will just give you some emphasis, which part that we are going to see often. Okay. So if we take the moment inertia as, if we take the definition, and if we take this YZ axis as to the Cartesians, so if we have our body as this picture here, let's say we have the rho, and we define the inertia for y-axis is defined by the z squared dA, and then we integrate the area, and for z the same, y squared dA, and then the whole inertia for the rho will be the inertia for y and inertia for z. We plus both of them. Okay, and inertia for the body or the rho, it's just the rho squared as that distance and then dA. Okay, so this is very, I think, I'm not sure whether you still remember or not, the inertia. So this is, we call the moment inertia with respect to y-axis, and this part here is the same but with respect to z-axis. And this one is, we call the polar moment. Polar moment of inertia. So for the rectangle here, so we can have at least two basic shape, and we are going to see a lot in the examples and practices. So first is, we can make it into rectangular area, and the second one is as a circle. Now if we take the rectangle, let's say we want to find the inertia for the with respect to y-axis. So we are taking the y and then taking the z squared dA for the integral. So we are going to have, so we have here, this is the y-axis. Now we are going to take the inertia, because we are going to settle at this center. We take this from here to then h over 2. So from negative h over 2 until h over 2. And then inside will be z squared, and then the dA will be this b. And then we are taking the increment, small increment as integrations for the z as dz. So we take, because we take b as a constant, or here is the base, and the height will be the z, and we consider the z for our integration. So we take the z squared, we integrate with 1 over 3 z cubed, and then b as constant, and then we put in the h over 2, put here, we get the bh cubed over 12. And this will be, you will see this a lot, and I will not going to repeat how we get this, so you should be able to understand the inertia for the rectangular shape will be the bh cubed over 12. Okay? And you will see now when we tackle some problem, we're going to use that formulation for the inertia. And then we could define as well for the z, which means the h is a constant, and b will be the one that we take the increment, and we just switch the h and b. But it's still the same. It's still the same. You could say that z, maybe you could just switch over the axis. I think it's still okay. Or to make it simplified, maybe you could just use this. And whenever you can define the height and the base, you can just switch over. Basically, the cube will be the height, and the constant will be the base. But if that is going to be, maybe you want to switch over, depending on the case, you can make it the height as constant, and base is your integrations, the small integration. And then the polar moment. We take it similarly as we did from the rectangle, but the difference is we are going to take from the center from 0. Now we are using the polar. So let's say this is our radius, and then we take these differences for the rho. And then we get this definitions. So by definition, the polar moment is rho squared dA. And then we take the integrations from 0 to r. And by that definitions, we are going to... So how to get this? This actually, if you could see this picture here. So we cut open, and we see that you can make it a rectangle. It's actually a rectangle, base and height, and the circumference, that is going to be the base, and the height will be the d rho. Okay, d rho. That will be the height. Well, let me write here. So this will be, you could take this here, and this could be here. So this will be the rho. This will be 2 pi r, right? The circumference. Okay, and that's why we get this. Okay, that's how we get the dA. So this will be dA, and we now change to the rho. So we are going to integrate the rho cube. We get rho 4 with power of 4 over 4, and then we cancel, it's over 2, and this will be r with power of 4. So we could have that as our polar moment, or if we're using the diameter, we could just change r with the diameter. So diameter over 2, which because of the power of 4 will be 16 multiplied by 2 is 30. Okay? So this is again similar with the rectangle. This is going to be, we are going to see this for some time. Okay? So I think the example for the chapter 2, after some part of the design, which is going to be the allowable design, stress, shear modulus, and then we are going to see the relations with this inertia. Okay, later we are going to explain. So that's the inertia for rectangles and for the circle. Okay, just a quick review, and now let's move on to what we call the general definition of stress and strain, and this will be the supposed it is going to be the last topic for the chapter 2. So after this we are going to chapter 3, which is the axial deformation. So let's imagine if we want to define the normal stress and shear stress at some point. Okay, let's say we define that at the point P. So let's say we have a random three-dimensional body, and we cut this part here, which we imagine through a plane, and then through that plane we define with some rectangular shape for this small rectangle, and we define that at the smallest rectangle here, which we define as a delta A, we have a point P. Okay. And then, since we applied some forces that is going to exert within the body, let's say the plane, we call the plane N, and it's supposed to be the normal. So the normal will be that way. And then we have this, we call it delta R on this small rectangle. So let's define this, and so this is the normal vector. So we start by the force factor. The force exerted at P, and on let me write infinite small delta A, okay, of an plane. And the magnitude delta R, and from those delta R we could see that we are going to have the delta F and the delta phi as a components of the delta R. So let me write here that the delta F and delta phi resolve into normal and tangential component. Or let me write, maybe it should be delta R resolved into normal and tangential component, which is delta F and delta phi. And then the delta V, we can also resolve this delta V with this delta V S and delta V P. So we introduce a new direction here. So we are going to define the normal stress and the shear stress based on all these directions. Okay, so directions for the N, the T, and S. Okay. So the first one is the normal stress, or the sigma N, at P, we define as limit as the delta A is going to be 0, as going to be really, really small, so that you can imagine the force will be concentrated on a small, small pieces of the A. And then we have the shear stress for NS. So the plane NS will be, take this. Okay. So N and S, this is the plane here. So the stress will be defined as a delta Vs, the delta Vs at this plane here, which is going to be here, defined by the delta A. So this will be the stress here. And then there are another shear stress, which is NP. This is NP, which is the PT. Okay. Defined by here, the NP. Okay. So shear stress, we have the Vs and Vp. From this N plane, the N plane, for the N plane. Okay, so that's one definition. And of course, in our course, we always state the sign convention. So, sign convention, we could state as usual. All the directions that is going to be the same with these vectors, they are typically a positive sign, and the one that is opposite will be the negative. So usually we design the convention as that. So positive for for N similar or maybe positive for direction similar to N, T, and S. So if there is a negative, it means that it will be opposite direction of that plane, okay, from that delta A. Okay, now if we now see the stress resultant, okay, so this is supposed to be the stress resultant. Let me write here. So this equation will be a very basis equation that is important for relations on stress on the area. So if we look on the figure, the new figure here, we could see some another definition that is built up from the normal stress and the shear stress, okay, which we define as the sigma x and the tau xy or tau xz. So the stresses on the small element delta A, as we mentioned here. Now we have delta A here. Now since we have the definitions stated by using the limit, that delta F over delta A is our normal stress. Now we could write the component for the forces in terms of this stress. Okay. So we say that the delta F will be the normal stress multiplied with the delta A, and the same thing with the delta V or Vy and Vz within this formulation. Okay, using the definition from the limit that we have before. So from the limit, we have the definition for the normal stress and the shear stress, and now we have the definition for the forces, component. If we have the random body of a three-dimensional body, and then throughout this, we could also include what we know as the moment. So we have, for all the shear force, we have the moment, we call it the bending moment. The bending moment for the mz, for the z-axis. So this is the moment that is going to circling around the throughout the z-axis, and this will be the bending moment of the y-axis. And T will be we call the torque. So this will be the torque. Or we usually say this will be the twisting moment. So if we try to write all of this into a new equations, then we can write this as, right here, let me write over here, we can write the force resultants. We take the integrations with respect to A and then just multiply. And how we define the dA? Since we know that in reality, all the materials, they will have, or all the geometric shape, they have the inertia. So the dA could be defined through the inertia. So we could use for rectangle, for example, bh cubed over 12. We could exchange the dA and then take the b or h that will be our integrations. Depends on the shape, which is the rectangle will be like that one, or maybe going up like that. Depends. Or a circle. We take the circle using the pi r or pi d to the power of 4 over 32. That will be the inertia, and then the area will be changed to respect to the radius. It could be the circle also. It could be rectangle to the circle. Okay, so we could define the F, the V, so the normal force and the shear force for the Vy, Vz, and we know in 3 dimensions. So far, what we have before, we see from a simple structure, and usually it's a 2 dimension. Now we are going to see in 3 dimension, and still there will be some simplifications to make our computations not too complicated. But now we are going to include this dA, which we can define as part of the inertia, And for the moment, the difference on the moment here will be the torque. Okay. Now the torque we have is 1 tau xz and minus z tau xy. This will be a twisting moment for the sigma mx. Okay. So if we could see from the case here that suppose that we have the y and we have the tau xz, which is going to be here. So this is actually the tau xz this is going to be this here, and y will be there. So v is here, so it's going to be like using the right hand rule. So it should be going to be here, okay, and then z and tau xy, z and tau xy is here, but z is going to be there, okay. So vy is there, and vy is z. This is y. That is z. Okay. So z also going to be over there. Okay. So this will be the moment, or so this minus or this minus that one. And this one is similar from the sigma x. We could see this rotated, so we could see the rotations through the z, or this through the y. So we are going to use more the right hand rule to let me write here. To establish the sign convention. For T and M. Okay, I think we are going to have a break. Okay, just a few examples on how we could use the inertia, or the general definition for the stress and strain, or now for the stress, for the normal stress and the shear stress. Let's say we have a stress distribution as in the figure on the right side, and suppose it is given that we have the sigma x, the normal stress in the x-axis, which is cy minus dz plus e, and then the tau xy will be 0, and tau xz will be equal to f multiply b over 2 squared minus z squared. Okay, I hope my z has a middle cut through, so it's going to be different from 2. So what should we compute is, we need to determine the internal system, or the net internal force system. So there will be, in general, so generally at the cross section, we could see there is v, vy, vz for the forces, and for the moment we have torque, the my and mz, the bending moment. Okay, now as we derived before, that we could have the forces, which is this integration of sigma x dA, right? And then we have the sigma x defined as the cy minus dz plus e. So the constant will be, so maybe let me write here. So C, D, E are constants to make it easy. So B, C, D, E as a constant. So we are going to have C integrations A, Y, dA minus D integrations Z, dA plus integration E dA. Now, how to integrate this? We could define y as y bar. So based on the centroid of the masses. And this will be z bar So since the origin of y and z is at the centroid of the cross sections, which is at the middle point, then the y bar equals z bar, since the origin is at centroid of cross sections, right? And the origin at the centroid means that the y bar and z bar will be equal to 0. So this will be 0, 0, and the rest will be E multiply A, or the area will be based on the B and H. So this will be equal to E, B, H. So this is F. Now phi y is 0 because the tau xy is 0. So we only have the phi z. So let's write phi z. Let me write here. Make it small. So v z is integration of tau xz. Let me write here phi y is 0 because the tau xy is 0. Now phi z, based on the formulations, is f. F is the constant, or let me write here, f is also constant. And then integrations with respect to a, b over h squared minus z squared, and then dA. Okay, now we know that the integrations with respect to a, z squared dA will be equal to hb cubed over 12, and the y squared dA, the inertia that we have before, this will be bh cubed over 12. Now we could imply this into our equations. Okay? So we multiply this phi z equal this will be fb squared over 4, and then bh minus the z squared will be hb cubed. So f hb cubed over 12. and this will be FHB cube over 12 minus FHB cube, over 4 minus over 12. So we have a 2 over 12 or 1 over 6 HB or FHB cube. This is Vz. Okay, and then the M and the T. So let's start from the torque. So torque is this will be Y tau xz dA minus z tau xy dA. And then the Y so we have FB squared, the tau xz is FB squared over 4. So FB squared over 4 integrations y dA minus and I think we could agree that the tau xy is 0. This is 0. So I think maybe no need to write here and just write 0. And since this is equal to FB squared over 4 y bar A and y bar is 0, then this is also 0. So the torque will be 0. Since we define here that the y bar and z bar is 0 because they are on the centroid at the cross sections, which is 0. Okay, now the bending moment for y. This is z sigma x dA. Sigma x will be this, so we are going to write all of that. So C integration, so I will just write all the components here. So this will be A y z dA minus d, this will be z squared dA, and then plus E. Okay, basically just making this yz and then making it the yz, and then define with the z here, multiply with z, this will be yz, and z multiply with z, it becomes z squared. Okay, and then this will be 0. This will be 0 because of this y bar and z bar. And then we only have this, the middle part. Okay, so we write here negative d over 12 hb cube in our inertia, right? So negative 1 over 12 d hb cube. Okay, this is the bending moment for y. Let me make it a bit small. Okay, and then lastly, it's going to be the mz. And based on what we have here for the mz, it should be so mz is going over there, stress resultants. So it's supposed to be if we have here the sigma x is on that part, it should be negative, right? So sigma x multiplied with y is over there, should be going up, and this will be here, so it should be negative. So let me write here, this will be negative. So this will be negative c y squared dA plus d yz dA, and then minus e y dA. And then based on the information that this will be y bar and z bar, this will be 0, and this is also 0. So we only have this negative c over 12 bh cubed, or 1 over 12 negative bch cubed. So in summary, we have all the net resultants, which is the f. The phi y is 0. The phi z is 1 over 6 f hb cubed. T equals 0, my is negative 1 over 12. And mz also same. Okay. Perhaps it's not intuitively understandable because of the variable and constant that is not really a number, but maybe if we could write a more clear calculation using numbers, maybe that will be better. Okay. One more example, just to show you how we can apply all the relations. So another one is here. So we have a rectangular bar, and at some cross section, there are tensile stress with magnitude we call the sigma 0 over the bottom half, okay, of the bar. And then after that half, it will be going to be 0 linearly. So it will be a linearly 0 at the top, at the cross sections, okay. And the cross section is you can see from the left figure. So it has defining the middle part, which is this is going to be the B, and this will be the B over 2. This is height, and the half, the h over 2, is a constant sigma, but the another h over 2 will be a distribution sigma. It has a distribution sigma. And it has the centroid here, the R. It's the centroid, which we have the height for the centroid will be the YR, which we are perhaps, we need to figure out the YR, how is the distance. Okay. And then we have a, so the question is, we need to express the 6 stress resultants. So which means that this F, the phi y, phi z, the torque, the my, mz, that will be the questions. And the last question, if we replace the normal force and the moment mz, and we replace by a single resultant force, as in this figure, the force will be placed on this YR, so with this height. So what should be the location of the YR? What is this new YR? So first we are going to describe this or observe the first question, finding all the 6 resultant, which we can do that by taking the F. So finding, so let me write here, finding the 6 stress resultants. So first is F, will be the integration with respect to A of sigma x dA. So if you could see the F and the sigma x, since we have this distribution here, we can separate this and this triangle here. Right? So we can separate the integrations. So first, we could do it directly with the rectangular. So we could take this sigma 0 and then multiply with the base and h over 2. Okay, no problem. And then we need to plus the h over 2 integration. So h over 2 until the h. Okay, so this so to help, maybe here is we can draw an axis here. This is h, this is 0, this is h over 2. So from h over 2 to h, so b or let me write this as b as a constant. And then we define the the h and the b over 2 and yr. So we write here this is going to be 2 multiply sigma 0 this is y. So y over h. Or let me write here. So this is going to be that way. Okay. 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 So based on the triangle, we have 1 minus y over h. This is dy. We take the integrations. So 2. This will be h over 2. After we have some calculation here, let me just going through this part. And then we have so this will be 3 over 4. Okay, so that will be the f. And there are nothing in the information about the tau. So the tau xy equal tau xz equals 0. So phi y, phi z is 0. So we don't need that v. And since this 0, the t also will be 0 since this tau is 0. Okay. So then we can only calculate the m, and since the sigma is symmetric in z, then this will be also 0. So this will be my, that is 0. So mz, then the only bending moment that we can find is going to be negative y sigma x dA. And again, the sigma x, it's based on the same reactions, the same formulations. Let me write negative b now we can complete everything here. Sigma 0 y dy plus h over 2 h 2 sigma 0. Now 1 minus y over h. This is from the centroid. And then y dy. Okay. And then this should be multiplied with everything here. Forget to make the bracket. So the b should be calculated with this everything. And this will be equal to so we calculate this, we get negative 7 over 24. Okay. Okay, that's the mz. Okay, so the only force that we get is only F and the bending moment with respect to Z. Now, if for number C, if the F is replaced and then we place that on the YR, so this makes the MZ as negative YR F. Okay. And then we have the the resultant for the F blocks. So first is from the triangle. The triangle part is this. This is triangle. This is the rectangle. So we have, this will be, let's say the F for the triangle, let's say this is F2. So this is 1 and this is 2. This will be sigma 0 BH over 4. And we have the F1, so that is for the rectangle. This is sigma BH over 2. And now this height for the F1 will be the middle point of H over 2, so this will be H over 4, right? And the triangle, this should be two H over 3. This is H1. Let's say H1 is H over 4. And this is the H. So we could also see that the F1 Y1 plus Y2 F2 is YR F. And if we compute the F1 F2, multiply everything, this should be equal, and we get the YR will be 7 over 18H. If we take all the stuffs and we make into these equations, and we get the YR should be 7 over 18. Okay, so far that is the definitions for in using the inertia and also the centroid of the masses. Okay. Next one is actually the strain, the extensional strain, but I think let's keep that for next week. Perhaps just a quick review. Let me go back a little bit here. What we have in the details here. How about we try this one just for warm up for tomorrow? Okay, can you see this one? Chapter 1 for 1.4 problems 14. So this is supposed to be having a distribution loads. But I think this a little bit to understand this, well, let's say we take the the bar. Okay, we take the bar. Okay, we have the W here. And we have we only have By for the reaction at B and Cy, right? Because it's a roller. So that is only the reactions that we have. And then both ends, they are having, let me write here, maybe make it small. And we have the distance. Both are this distance A. So determine the expression for the location A for the two supports that will minimize the maximum bending moment M max in the beam, and determine the value of the M max. So to minimize moment max, we pick, the whole thing, I forgot the whole thing is L distance, right? We pick A over L, that the moment max is equal the M on A. This would be equal with the M max 2, which is the M2 L over 2. Now, if we see from the let's say this 1 and 2 is my definition for the diagram that we are going to take. So let's say we define the M1. So define M1, that is going to be from 0 to A. So let's say this is going to be the X. So this is in between 0 and A. So let's say we have a new distance X. And we have the distribution load, which is the W0. And the internal resultants, we have the V1, F1, and the M1, right? Now, based on what we have here, we can take this sigma M with respect to 1. Let's say the point 1 is on the endpoints here, which is in the X distance. This is 1. So let's say this is going to be equilibrium 0. And suppose that we have that positive directions. So we have negative M1x, and then we have negative W0x, right? W0x, that is supposed to be the at the end points, and then multiply with the x over 2, which is this one here, So this will be, let me write with different color. So this will be W0x at x over 2, right? So we need to multiply with x over 2. This is equal 0, so m1, this will be negative W0x squared over 2. Okay, now we define the second one, the M2, as the rest of the diagram. So we define the M2. So define the M2 as it's from A less than X less than, let's say we have the L minus A for the right side. So this is the one here, and this is the second one. Okay. So write over the diagram. So we have the same distributions, and then we have here we have the by. Oh, I forgot to mention, we could make the symmetry that, because this is all the same distributions, we could say that by is equal with cy, okay, and we could write that based on the calculation of the W0, this will be W0 L over 2. Okay, so if we cut into half, we could see that cy and by will be equal, and this will be W0 L over 2. I forgot to mention that. So this will be W0 L over 2. And this will be distance A. This will be the V2, M2, and F2. And the same, we take the sigma m at 2 equals 0, and let's say this is going to be 2, this point on the right, and let's say this is going to be positive, so negative m2, and now we have a new x, so this is new x here. So m2x, and then plus the, oh, we have another W0 L over 2, or WX, sorry, WX here, and this will be x over 2. So let me, this is the minus W0x x over 2, and a negative W0L over 2, or plus, sorry, plus, right? And then this will be the x minus a equals 0. And how to solve this? Basically, we are going to set these two equations, the M1 and M2. So we set the negative M1 at A based on this one, okay, and M2 at L/2, and then M2 L/2. So basically, we are going to substitute all the x with A for M1 and L/2 for x at M2. So this will be A squared over 2. And then we solve this, canceling all the same variables. This will be oh, let me write. I forgot to write that M2 will be negative that. Okay. So we multiply here. Okay, so basically we solve this, and I don't write the final answer. We solve this to take A equal something. Okay. You can see that we can cancel W0, right? And then we can also calculate the L, or not calculate. So A will be in some formulation with respect to the L. Okay. I think later on we are going to still we are going to see this this part of the problem, and then we are going to take the, so this is going to be the loads. Okay, so this is going to be the loads, right? And we are going to take these loads and write as the V, as the shear, and then we could write as the moment. Later we are going to have some methods, and what we have here is basically we can write the V, and based on all the resultant in this point B and C, we're going to see that we have this is going to be negative at cis, and then it's going up, and then it's going down, it's going up, and then it's going down at this certain point here. It's 0, which basically based on the integrations. We are going to get into this part later, but I will show you what we can do from this. And here basically we take the integration for this. You can imagine, if you remember the calculus, the linear, if we integrate, it will be a quadratic, right? So this will be going to be that, and then it's going to be that, and then this will be 0. Okay. And this will be the M max 2, this will be the M max 1. But we don't really need that. This is just to show you. Later we could do this, okay? But how to solve this is actually taking the moment that should have equal value when we pick the So when we slice the bar at any point, that the slicings, it makes the resultant for the M max for that one particular bar is equal to the other one. Okay. Of course, we could slice anywhere. Okay? We could slice anywhere, but since we have asymmetrical, then we could take, and we want to know the A, then we could take the first one is here in between this distance, and the second one is perhaps we take the rest and then we slice up until this one, okay? Because this is the same A, or the same distance. So we could observe from these two bar, which has the M1 and M2, which we take equations equaling both of them and write down the A in terms of L. Okay, I think that will be end of the class. I think tomorrow at least one questions about the distributions like this, but not as complicated as this one.